Okay, so we've looked at a couple of special cases. We looked at the case where we had a perfectly clean alternative, and we said we will definitely choose that in the long run, and that is proved in the paper. And we also looked at the case with Cobb-Douglas production function and this very simple damage function, and then we said in that case emissions will be constant in the long run. They will level out at some constant level. But can we find some more general rules about what is going to happen in the very long run, especially if there isn't some perfectly clean alternative? Because for local pollution, you might think, like for lead in petrol or sulfur dioxide emissions in electricity generation, you might think there's always going to be an alternative which is like perfectly clean. But when we're thinking more about global pollutants, carbon dioxide, and if we're going to apply this more to things like biodiversity and land use and so on, it seems clear that there aren't going to be perfectly clean alternatives. There's always going to be a downside for the environment to our activities. So how is that going to play out in the long run? Can we say anything general about that? It turns out that we can, and that's what we're going to look at now. And we do it by defining two elasticities. Okay? The first one, eta, is the elasticity of substitution at the optimal pollution level between X, consumption, and Q, environmental quality, in the utility function. Okay, and what is an elasticity of substitution? So an elasticity of substitution, an elasticity in general is a sensitivity, right? It's, sorry, wrong pen. It's an elasticity is in general a sensitivity of quantity to price. An elasticity of substitution is a percentage change in a relative quantity divided by a percentage change in the relative price. So the elasticity of substitution between X and Q is like how willing are we to substitute between quantity of consumption and quality of the environment given a change in their relative prices. If that elasticity of substitution is high, we're like, the environment's crap, but it doesn't matter because we've got loads of consumption. If it's low, it's like, like quality environment's crap, and sure we've got loads of consumption, but we really want both, so we're not happy. Okay? The second one, sigma, is the elasticity of substitution between P star, at P star, between A and P, where A is productivity and P is polluting emissions. So, sorry, I'm just going to pause here. Sorry, I got momently confused by my own notation here. So A is the aggregate input. It's like ALL. It's the labor capital aggregate. So this is the elasticity of substitution between aggregate inputs, A, and pollution, P. So it's like if the price of pollution, so elasticity substitution between A and P. So it's like if you say to the firm, look, there's not much net inputs A, but you can have loads of pollution. If they're happy with that, that's the high elasticity, right? It's like, or alternatively, again, if the elasticity is high, look, you can have loads of net inputs A, but you're hardly allowed to pollute. If the firm is fine with that, that's high elasticity. But if the elasticity is low, it's like, oh no, then we can hardly produce anything. We need to be able to both pollute and have lots of inputs. That would be a low elasticity, an inflexible firm. And the key proposition in the paper is that the direction of change of P star when A increases depends on which is the greater of eta and sigma. If eta is greater than sigma, P star increases, and if eta is less than sigma, P star decreases. So what's the intuition? High eta implies flexible consumers who are happy to trade off low environmental quality against high consumption. High sigma implies flexible firms who can easily substitute between higher labor capital inputs and lower polluting emissions. So if consumers are inflexible, low eta, then when A rises, driving up X, inflexible consumers demand an increase in Q and flexible firms reduce P. Okay, so we want consumers to be inflexible and to demand a combination of higher consumption and higher environmental quality, whereas firms are flexible and can relatively easily cut polluting emissions while increasing production. Then we get the good outcome and declining emissions, and vice versa. So if we have in the limit Cobb-Douglas production function that sigma is 1 and damages that increase linearly with GDP, eta is 1, then pollution approaches a constant level. So that's the special case we saw before. Okay. And there's proofs for this in the paper, but actually they're pretty long and pretty hard work. Then it's nothing that sophisticated, but it's pretty damn hard work, so I'm not going to go through them. But basically what this is showing is that the key in the long run is these relative flexibilities. If consumers are like, oh yeah, it's fine, then we can expect like worsening environmental quality, and while we can increase consumption. Or if consumers really demand both, then they will get both, depending again on the flexibility of the firms at the same time. And of course, assuming that we're in some kind of democracy or whatever, and that the will of the people is reflected in policy, which is another question that we'll talk about a bit later on. Okay, so that is the core of the theory. I'm just talking you through it. You can do look at the paper, but the proofs are actually quite involved, so I don't think it's particularly useful to go through them. What we'll do instead in the next video or two is to go through a specified model.